Okay, so now let us look at a couple of applications of depth first search. So one thing we can do is to decide whether a vertex is an articulation point or not for a graph. So what is an articulation point? So if I remove a vertex from the graph, does the graph get disconnected? If so, we can call the vertex as an articulation point, otherwise not. So for example, if I remove vertex 1 from this graph, it's going to get disconnected to two components in the sense that 2, 3, 4, 5, 6, 7 are going to be in one component, 8, 9, 10, 11 are going to be another component, and they are not going to be reachable to each other. On the other hand, if I remove 7 from this graph, the rest of the vertices are going to stay connected as one component. Okay. So 1 can be called an articulation point, whereas 7 cannot be called an articulation point. So a brute force approach to decide whether a vertex is an articulation point or not is to simply just remove the vertex and see whether the graph gets disconnected or not. But in the algorithmic point of view, in order to see whether the graph remains connected or not, we have to either run breadth first search or depth first search, which is a time consuming process to do after removing each vertex. So what we want to now do is run just depth first search once on a graph, on a connected graph, okay, and see and use the results of depth first search to classify the vertices as whether articulation point or not. And we could do that. So that's what we're going to see. Now, before we do that, let us look at some rules for classifying a vertex as articulation point or not. So the rules are kind of based on how the vertices get classified on a depth first search tree. So let us use an example and then go back to the rules back and forth. Now, the result of depth first search, we get what is called a depth first search tree, where we have the starting vertex as your root, and then the tree edges, and then the back edges put together will constitute a depth first search tree. So we saw this example last time on this given graph, and at the end of the depth first search process, we classified the edges as tree edges and back edges. And now also I said what's a leaf node and internal node is. So an internal node is the one that has at least one tree edge further down and a node attached to that. So 1 is an internal node because it has at least one tree edge, or actually two tree edges further down. And then 2 is an internal node because it has at least one tree edge further down. And 3 is an internal node because it has at least one tree edge further down, and so on. Now 4 is not an internal node because it doesn't have a tree edge further down, so it is a leaf node. We can also think about it like this. So node 1 has two child nodes, so we can call a node as a child node if it comes from a parent node to a tree edge. Okay, so node 1 has two child nodes which are 2 and 8. Node 2 has one child node which is 3. 3 has two child nodes which are 4 and 5, and so on. Okay. Now you can also say so that node 4, the leaf node, has no child node, so no leaf node has a child node. Okay, now another thing is so we can call this the nodes starting from say node 2 and further down to constitute what is called a subtree for node 1. So node 1 has two child nodes, child node 2 and child node 8. So starting from child node 2 and everything below that can be considered as to form a subtree. Okay, and similarly this node 8 and everything further down can be considered to form a subtree. So there are two subtrees for node 1, each subtree rooted at a child node. So for node 1, there is one subtree rooted at child node 2. That means that subtree includes 2 and everything below that, and another subtree starting at 8 and everything below that. Similarly, node 2 has one subtree starting from its child node 3 and everything further down. Node 3 has two child subtrees, one subtree involving just a child node 4, nothing else, and another subtree involving child node 5 and 6 and 7. So The child node is said to be the root of that subtree. Okay, so for node 1, the two subtrees have root 2, and then this one has root 8. Alright, so that's about the subtree. Alright, so the rule for articulation point is this: leaf nodes are not articulation points. So that's one rule. And as I said earlier, if I remove a leaf node, the graph is not going to get disconnected. Okay, so leaf nodes are not articulation points. Now the second rule is this: the root node is an articulation point if it has at least two child nodes connected through the tree edges. Now in this case, node 1, the root node, has two child nodes. So the rule is at least two child nodes. So it has two child nodes, that's good, and enough to classify the vertex as an articulation point or not. So once child node is node 2, another child node is node 8. So you can classify node 1 as an articulation point. And you can cross check, because if I remove node 1 and all the edges attached with node 1, the graph is going to get disconnected. Okay, so you can cross check, remove node 1 and all the edges associated with node 1, all the tree edges and back edges that are incident on node 1. If you do that and see if the rest of the vertices are connected, no, they're not going to be connected. So node 1 is an articulation point. So we saw the rule for a leaf node, and we saw the rule for the root. Now what about the other internal nodes? So that's the kind of more detailed thing that we have to look at. Okay, so the rule for the other internal nodes is this. So let us take a general scenario, say a node U, which is an internal node. So it's not a root node, because we saw a separate rule for the root node. So the root node is somewhere further up, and from that root node you go through a sequence of tree edges and reach this internal node U. Okay, so above U you have the root node and and some more predecessor nodes if possible. So at least the root node is up there above U. Now node U has 4 subtrees, because you have 4 tree edges, so you're going to have 4 subtrees. So now in this figure you see from these subtrees you have a back edge coming out and going to a vertex above U. Okay, so from each of these subtrees you have one back edge going above U. So if you look at this, if I now remove U and all the edges incident on U, say these tree edges, all these 5 tree edges, now the rest of the vertices are still going to be connected because of this back edges. Okay, so from this subtree can go to this what's called the predecessor part, and then use the other back edge to come to the other subtree, and so on. So if I remove U and all the edges associated with U, the rest of the graph is still going to stay connected. So U in this case cannot be called an articulation point. Okay, so when can you call an internal node like U to be an articulation point? So again, look at this figure here. You have subtrees starting from U, and now there is this subtree, the one I show here. From this subtree there is a back edge that goes only up to U, and from the other 3 subtrees, like here, we have a back edge that goes above U. So now if you look at this subtree, there is a back edge that goes only up to U. So that means if I remove U and all the edges associated with U, this back edge will also go away. Of course, all the 3 edges associated with U will also go away. So when we do that, then this subtree gets isolated. So the vertices that are part of this subtree will not be able to reach the other vertices in this graph. So U can now be called an articulation point, because removing U will kind of cut off this subtree vertices from the rest of the graph. So when can we call U an articulation point? There is at least one subtree for that node U, such that from that subtree there is either no back edge coming out of the subtree, or there is a back edge that there are one or more back edges coming out of the subtree, but all those back edges go only up to you. They don't go beyond you. Beyond you means above you. Okay. So if there is no back edge that goes above you from any of the subtrees rooted at you, then no, if the presence of at least one such subtree from which there is no back edge, even if present, goes beyond you, it goes only up to you, then that vertex u can be called an articulation point. Now again, there is no need for such back edge from each of the subtrees. There need not be any back edge. In that case also use an articulation point. Now even if there is a back edge, the back edge should go only up to you, not above you. If there's at least one subtree like that for node u, at least one subtree, no need for every subtree to be like that, at least one subtree like in this case, because you see the other subtrees you have back edges that go above you, that is fine, but there's at least one subtree from which there's no back edge that goes beyond you, that is above you, then u is called an articulation point. Okay, so that's the rule. Okay, so let us apply these rules here. So we already classified the leaf nodes and then the root node. Okay, so the root node is an articulation point. What about vertex 2? Now from vertex 2 you have only one subtree, and from this subtree you have a back edge, this 4 1, that goes above 2. So because of that back edge, vertex 2 is not an articulation point. And you can cross check. If I remove vertex 2 and all the edges incident on vertex 2, the rest of the vertex graph is still going to stay connected. Okay, so there's only one subtree, and from that subtree there's a back edge that goes above 2. Now what about vertex 3? Now vertex 3 has two subtrees, one with 4 and one with 5. So from this subtree there is a back edge that goes above 3. Now look at this subtree involving this 5, 6 and 7. There are some back edges that begin and end within the subtree, and there's one back edge that goes only up to 3. Now, so there's no back edge from this subtree that goes above 3. So that is good enough to classify this vertex 3 as an articulation point, because there's no back edge that goes above 3 means if I remove 3 and all the associated edges with 3, 5, 6 and 7 are also going to get disconnected from the rest of the vertices. So 3 is an articulation point. Now what about 8? There is a subtree involving 9, 10 and 11, and there is a back edge from that subtree that goes above 8. There's another back edge that goes only up to 8, but there's this back edge from 11 to 1 or between 11 and 1 that goes above 8. So because of that, 8 is not an articulation point. So you can apply this rule for the other internal nodes also, like 5. 5 has one subtree 6 and 7, but there is like one back edge 7, 3 that goes above 5. So because of that, 5 is not an articulation point. So apply this rule for the other internal nodes, you will see none of them are articulation points. So only 1 and 3 are articulation points for this graph. So you can try one more example. So by now you should be able to run depth first search on a given graph and classify the edges as tree edges and cross edges. So we draw the depth first search tree starting from the starting vertex 1. From 1 you have a tree edge to 2, and then from 2 you have tree edges to 4 and 7. Now 4, from 4 you have tree edge to 3, then to 5, then to 6, and then you have the back edges. So now if you look at this, the leaf nodes are 6 and 7, they are not articulation points. Then the root node is like having only one tree edge associated with it. So the rule for the root node to be an articulation point is it should have at least two tree edges associated with it. In this case, one has only one tree edge associated with it. So the root node is also not an articulation point. Now node 2 has two subtrees, one with 4, 3, 5, 6, another with 7. Now from this subtree with 7, there's one back edge that goes above 2. And with this subtree starting from 4, there's one back edge also like 3, 1 that goes above 2. So from both the subtrees, there's at least one back edge that goes above 2. So 2 is also not an articulation point. What about 4? You have one subtree starting from 3 and there's one back edge that goes above 4. So there's 4 is not an articulation point. Similarly 3, you have one subtree with 5 and 6 and there's one back edge like 6, 4 that goes above 3. Similarly 5, 4 also goes above 3. So 3 is not an articulation point. Now 5, you have one subtree with 6 and there's one back edge that goes above 5. So 5 is also not an articulation point. So you'll see in this graph, none of the vertices are articulation points. So if a graph has no articulation point and it's a connected graph, then we can say the graph is said to be a biconnected graph. So a connected graph with no articulation points can be called a biconnected graph. Now what is a property of a biconnected graph? So in a biconnected graph, you can have two vertices joint paths between any two vertices, at least two vertices joint paths between any two vertices. So in this graph that we just looked at, and we saw it's a biconnected graph, no articulation points, and it's a connected graph. So you can just enumerate some pairs of vertices, and between them there are at least two vertices joint paths. Vertices joint paths means no intermediate vertex is present in one path is in the other path. So for example 1, 2 is one vertex joint path because we have an edge between them. Now 1, 7, 2 is also a path between 1 and 2. So the intermediate vertices in one path are not part of the other path. So for example between 1 and 5, 1, 3, 5 is a path, 1, 2, 4, 6, 5 is a path, and 2, 4, 6 are not part of this path, 3 is not part of this path. So they are vertices joint paths. So at least two vertices joint paths between any two vertices in the graph. Now what is the significance of articulation points in a social network? You can see if I remove a vertex, if I remove a user from that network, the rest of the users are going to get disconnected in the sense that are not going to be able to communicate with each other. If so, that user is an articulation point, otherwise not. Okay, so I have another example. You can run depth first search on this graph and you will notice that it's also a biconnected graph, no articulation points. Okay, so let's stop the video with this.